This is a Graham's law of effusion demonstration, and I'm using a simple manometer filled with water, colored, and to show you how the simple manometer works, because basically we're going to use this manometer to gauge effusion into and out of one side of the manometer. This is an open tube manometer on this side, and this one is closed, but it's opened to this tube on the side. So essentially it's a manometer that's opened on both ends. Atmospheric pressure can enter both sides of the manometer. Now, some manometer basics. I'm going to add a syringe, and if I pull back on the syringe, making the space smaller in the syringe, you can see that I'm going to lower the pressure in the air in this part of the manometer, and it's lowered by the height of the liquid being supported in a column. We have atmospheric pressure pushing down, and I've lowered the pressure. Now atmospheric pressure is now higher than the pressure in this side of the manometer, and we could measure that difference if we were to measure this in millimeters of water, convert that to mercury by dividing by 13.6, and then knowing that value in torr, or millimeters of mercury, we would of course take that value and subtract that by the atmospheric pressure in millimeters of mercury or torr, and we get the pressure in here. So this pressure is lowered, okay, by atmospheric pressure by this height and column. But if I was to reattach and let go, the levels will equal out. And if I was to do the opposite, push in and make the space smaller, I would increase the pressure for the same amount of liquid being supported. Pull back, making the space bigger, the pressure drops. And we can measure those pressure differentials. Here they're even, and it's important to realize that we're going to measure a pressure by how much the liquids move. Right now, of course, they're equal because the pressure on both sides is the same. Now, what I'm going to do is, because this is a Graham's law of effusion, I'm going to put a porous cup in here. This porous cup allows for the gases to go in and out of these small openings, and that's why it's effusion. I'm going to place this in a beaker, and right now the gas particles are going in and out of this container at an equal rate. Therefore, the pressure is about the same, although it looks like the pressure is somewhat lowered, but give it some time. Okay, so the pressure should be even. Give that some time. The pressure, the air going in, will equal the air going out. Okay, now what I'm going to do is I'm going to disrupt this balance of pressure by starting with a very, very dense gas. So I'm going to fill this container with sulfur hexaflouride, which is a gas with a density about 6.1 grams per liter at 20 degrees Celsius in atmospheric pressure. And we're going to see, comparatively speaking, how that compares with air. Now, air has a density about 1.2 grams at atmospheric pressure. So clearly, we're adding some very heavy gas molecules here. Let's, instead of talking about it, let's go do it. So I have a balloon here filled with sulfur hexafluoride, okay, and I'm going to fill this container with it. Let's go watch what happens in the manometer. Hold on. I'm just going to push the balloon, pushing it down. Again, it's a very dense gas. Just going to fill up this container like water. I'm adding a heck of a lot more than probably this flask. And a nice way to do this also is I could actually pour it into the beaker. Alright, so clearly I've added a heck of a lot of sulfur hexafluoride gas to this. And we can see that the levels, okay, are definitely changing. We can see that this one is definitely under lower pressure. Atmospheric pressure is pushing down greater than this side, so we can definitely see a difference in the levels. Clearly the pressure has been lowered. Now why? Well, the heavier gases surrounding this, and you have some heavy gas trying to go through the openings, and you have some light gas trying to enter, and vice versa. But the lighter gases are exiting the hole faster than the heavy gas can go in. So therefore we have more molecules leaving this system than molecules going in because of Graham's law of effusion. So the pressure has dropped. Okay? So let's reverse this by adding some helium. All right, we add some helium to the mix here. All right, let's see, we're going to add a gas that is very light, and helium, okay, now if we wait a little long, we have a lot of sulfur hexafluoride that's kind of going into the system here, diffusing in a slow rate into this area. So we have to wait a little bit, but we've got a great difference in pressure there. So I'm going to now add some helium. All right, now helium has a density of 0.17 grams per liter, so it's a much faster gas for the same kinetic energy. Both of these gases are at the same temperature. Now I have to change the structure of this, so we have to dump out the heavy gas, okay? And I've turned this upside down because this gas is very light. Okay, so filling this with helium, we see a dramatic increase in pressure. Now why? It's because the helium molecules, being so light compared to the sulfur hexafluoride in here, are going into the opening faster than the sulfur hexafluoride can escape. In this case, we're adding more molecules to the system, and therefore the pressure increases. A very, very interesting way to do Graham's law of diffusion, I think. Let them go down. Notice what happens. Helium escapes, okay, and we should retain our pressure balance again. Graham's law of diffusion. And the Graham's law of diffusion is about a difference of 6.04 rate. So helium escapes that opening 6.04 times, or it goes into the that porous cup 6.04 times greater than that of sulfur hexafluoride.